conference will now be recorded.
All right. Hello, everybody. Thank you for joining us for the Satellite Book Club seminar series. This is session number 71. Today's presentation promoting the use of the 1.38 micron channel from ABI and VIIRS. Our presenter, Dr. Andrew Heidinger, NESDIS GEO Senior Scientist, and our facilitator is Chris Gittro, the meteorologist in charge at the Weather Service Forecast Office in Duluth, Minnesota. Just a few reminders before we get into the presentation that this session is being recorded. There will be an opportunity for Q&A after the presentation, and we're particularly interested for comments from our field participants today. And that may include comments as well. You might have stories to share about the 1.38 band, and we'd like to hear those. We're always looking for future presenters, so if you have a different application, please get in touch with us, and the training team can help create training materials that may be unavailable or point you to ones you may be unaware of. And Brian Mata, the Office of the Chief Learning Officer, can help with that. I'd like to thank our Tower S team, particularly Kishad Bowman, Lee Byerly, our Office of the Chief Learning Officer in the GOZAR and JPSS programs, for their support of the Satellite Book Club. This goes off without a hitch every week because of their support. Without further ado, I'd like to introduce Andy, a long-term colleague of mine from University of Wisconsin and actually served on my PhD committee. He's currently the NESDIS GEO Senior Scientist and is working mainly in support of GeoXO. He previously worked at NESDIS STAR and led the cloud science team. His research included algorithm development, radiative transfer modeling, sensor calibration, and satellite climate analysis. Andy, welcome to the book club.
Great, thank you, Jordan. Thank you, everybody. It's an honor to be here. I've loved this series, and I'm happy to be part of it. So I'm going to talk about the 1.38 micron, and I'm going to give a little motivation of why I volunteered for this talk. I'll talk a little bit about the unique physics of this band and some of the imagery specifics about how this band can be scaled to reveal a lot of information. I'll give an RGB that uses this band, I think, to great effect. I'll talk a little bit about some of the other things beyond VIIRS this band can do, and I'll show an Arctic RGB comparison, and I'll talk a little bit about how we use this for products. So a couple caveats. I know I'm not a forecaster, nor have ever been. So I don't use AWIPs, so some of my imagery is handcrafted, and though I tried to match what I was told AWIPs shows. You may wonder why I'm interested in imagery. Well, you know, a lot of the level 2 work that we do, imagery is very important for kind of, you know, supporting and validating and just giving context. And I can't make things like geocolor images, which are all the rage. I want to point out that the 1.38 micron RGBs I'll show were made in 2017, and there's documentation made by Jarrell Torres and Scott Lindstrom, which I'll show. And I really heavily use the Sierra loop of the day with some guidance from Curtis Seaman on picking the scenes I'm going to show. And I think that's a really tremendous asset, because there is no archive of imagery that I know of. So, okay, so motivation. So Jordan Gerth's NWA 2021 presentation I show here, called Following the Observations, How Weather Satellite is Used at NWS Field Offices, did a neat study about which channels were used the least. And you can see here, the loser are the CO2 band, the ozone band, and coming up third to last was the VIIRS band. And my reaction was similar to John McEnroe. You know, you can't be serious here. So I volunteered to give this presentation to highlight some of the capabilities, at least that I see with the 1.38, and maybe get a discussion going, because this band, as I say here, you know, will be on the GeoXO most likely, and will be around for a long time. So a little bit about the physics. I made this figure here. what it shows are the band passes in colored. So that MODIS had a 1.38 that was, over 20 years ago, and VIIRS has one, and ABI has one as well in blue. And you can see the VIIRS and the ABI are much more centered than the MODIS. I show also these transmission spectra over the 1.38 micron region. So this is for the whole atmosphere. So 0 transmission would mean you can't see the surface at all. 1 transmission would be you see everything. So you can see these bands are all centered in kind of the valley of this feature. MODIS, however, was quite a bit broader. And so sometimes you would see the surface and there were some instrumental issues. VIIRS and ABI, though, are much better centered, and they really perform very, very well. I showed, too, the subarctic winter profile. So subarctic winter, of course, has less water than the tropical, so the transmissions are greater, so you might see the surface on a very dry atmosphere. However, I'll say that for ABI, typically we view at high angles, so that the higher the angle that you view at, the more the water vapor on the path. So that really isn't a problem with the ABI. So yeah, that's what I want to say about the physics. So here I show just kind of a broad brush look at all the visible channels for a scene, again taken from that Sierra Loop of the day, May 27th, 2019, northeast of the USA, in the surrounding Atlantic Ocean. So if you just look at the 6 solar channels, scaled as Lee told me they were in AWIPS, the 1.38 stands out as kind of being this boring, dark, featureless image compared to the others. And maybe that's why it isn't used very much. I mean, you can see from this image that the low clouds disappear because there's enough water vapor that you don't see any of the low features. You can get a hint of where the cirrus are, but it's not really very compelling. So if I go to the next one, so you can really, as I mentioned, the 1.38 micron channel on both VIIRS and ABI performs very well, and you can scale those from the default AWIPS. You can decrease the range of the data and really pull out features. So here I show in the upper left the default AWIPS scaling for this, again, this Northeast USA scene of 0 to 50. But then as I crank down the knob, 0 to 10%, 0 to 4, and 0 to 1, you can see that there's this, the cirrus features very much stand out. And there, for example, there's this cirrus feature in the middle that's hard to see in the 0 to 50%. And, I'll go back, was entirely absent in any other channel, any other solar reflectance channel. But even at the 1% level, you start to see the noise of the observation, but the details of the cirrus, are much more revealed. So I think it's a very important thing to those who want to use the 138, scale it appropriately to pull out the features. And even from my experience, going down to 1% max is often instrumental. Of course, you guys are experts in using AWIPS and all the channels every day in ways that I can't argue with in any way. So I did try to look at the same scene. This, again, the 1.38's in the upper left, but you might look at it in the water vapor band or a brightness temperature difference or in a window channel. And I did scale these the best to my ability to pull out those features. And I think you do see it in the brightness temperature difference a little bit. You certainly see contrails and things pop up there. You do see it a little bit in the 11 micron image, but it's hard to see in the water vapor and hard to really distinguish what's water vapor emission versus cirrus emission. But again, the 1.38 for this dense cirrus case certainly stands out from the other channels. And again, this is a very subjective statement, so I'm sure, you know, you may have your own recipe for pulling out cirrus, but I think for the thinnest cirrus where there's not much thermal signature, the 138 is going to be hard to beat. And I'll just show an image here, a loop that I made, again, on the 138 on the right and the visible channel on the left. You know, again, just showing these cirrus features just popping out of the 138 with contrails and things like that. Low clouds generally disappear from view in the 138 unless there's a lot less. It's very, very dry atmosphere above. So let's talk a little bit about RGBs. So I think, from my understanding, the very famous one is the day cloud phase RGB. Shown here again, I took a slider image of the day, loop of the day from Sierra to show this. This is a South American scene called Cirrus and Smoke on the southern edge of the Amazon rainforest. It shows the this RGB with red is 11 micron, blue the visible, green the 1.6. It's very, you know this more than I do, it's a very well used RGB for cloud evolution. It's made by JMA, and of course JMA on its AHI, they chose not to have the 1.38. So of course they're not going to make an RGB that uses the 1.38. So I was a visitor of EUMETSAT during this time, 2017, and their next series has a 1.38, and they were very keen on making an RGB to use it. So we came up with the following RGB, which we called, again, it's conversion evolution. I don't think we knew of the other one, but it's very similar. So we named it Cloud Type RGB, and that's what the documentation from Jarrell and Scott call it. So I'll use that phrase here. But it uses the same channels except replaces the 11 micron in the red with the 1.38. And EUMETSAT's got a description of it, as well as we have quick guides. So I use here the 10% scaling for the RGB. And you can see, I'll go back and forth, you know, it just pops out the cirrus where the phase RGB doesn't show it, but the type does. And, you know, it's up to you whether or not this uber cirrus signal destroys the use of your phase RGB or not. But if you want to see cirrus, I think this might be a better RGB for that particular application. And again, I'll show that Northeast USA scene with these two RGBs side by side. You can see, again, you know, the very thin cirrus are very evident on the right, not so much on the left. You know, you can see that central cirrus in the middle, and it is the cirrus passing over the lower clouds and coming in over the Great Lakes. So, and this is also a simple RGB that, just like the cloud phase, there's no additional information used. It's a single observation and a single bin. I'll say too about this RGB that it works in the polar regions and it works for VIIRS. So VIIRS has the same channel set. And here, this was an image that the cryosphere team asked me to make over Hudson Bay, so quite north. And you can see the VIIRS on the left and the A8 ABI from GO16 on the right are very similar. But the great resolution of the ABI shows it's even valuable at these very northern latitudes, which I think is interesting. And you know, if I were a forecaster, I would certainly choose the ABI over VIIRS for this scene. And this RGB, both of them, sea ice are very green. So you can see more than cirrus though. Here's again, I go back to that loop of the day, cirrus and smoke in the Amazon. On the left is the 0.47 micron band from ABI, which I assume is what people use to look at smoke at. It's where smoke is the brightest and the surface is the darkest. You can see there's fires in the southern edge, and there's smoke signatures, but they're kind of obscured by the cirrus. See, maybe it's hard to tell what's smoke and what's cirrus, what the movement is. But if you look at the 1.38, which will only show the cirrus, you can clearly see what features in that 0.47 image are caused by the cirrus and what are caused by the smoke. So if the smoke is low, the 1.38 I think is very useful in screening out the effects of cirrus. So you can see the cirrus separately from the smoke and therefore deduce where the smoke is going better, I would say. That's not always the case. Sometimes the smoke gets high up in the atmosphere, and once it does, the 1.38 is probably the only channel that will show you where it is, because smoke is comprised of very small particles which are entirely invisible to any infrared measurement, and it's harder to see at 2.1 microns. So here is an example, a visible image of a smoke scene from the west that's been lofted, and on the right is the same 1.38 image. So this is unfortunately not an animation, but you can clearly see that, you see the smoke plume that you can kind of see in the visible, but it really stands out. You could even see smoke kind of streaming in from the northeast, I think, as well. That is clearly, is this not hard to see, I would say, in the visible. Of course, I'm not an expert. Maybe you've tuned your eye to this, but the 1.38, again, I think if the smoke is lofted or anything is lofted, dust, ash, you're going to see it in the 1.38. We did make another RGB for the JPSS cloud demo in 2017. In this one, we dropped the 0.65 in the green and repeated the 1.6. So it's really a 2-channel RGB. What this does is low cloud is cyan, high cloud is red, but the nice part is sea ice and the sea are totally black. So you won't, if you want to track clouds over Greenland and know if they're high and low, this is proven to be a very effective RGB. And I'll just show an example here of one day, July 31st, 2018, of combining NOAA 20 and SMPP. Again, I'm not an expert in true color, but I made a true color-ish image on the left, and I show this RGB on the right. And if you just notice, like over Greenland in the middle of the Arctic, it's hard to see in true color necessarily the cloud ice boundary, but here it does it very, very well, and it gives you the additional information from the 1.38 that some of these clouds are high, which I think is also, it's harder to use these thermal bands in the Arctic because of the thermal structures in the Arctic. So I'm coming to the end of my time. The level 2 products also make use of the 1.38. So the enterprise cloud mask that will be coming into operations is machine learning. So as is true of most machine learning approaches, they can pick and you feed them a bunch of observations and they pick and choose the ones that they want to use. And the 1.38 always makes the cut. So it is an important channel for cloud detection. We do also make a thin cirrus mask from the VIIRS heritage. That's basically a mask made directly from the 1.38, and that's useful for several of the algorithm teams. The aerosol team also uses a 1.38 in their dust detection logic. And the cloud team that I used to lead often also makes a cloud optical depth from the cirrus, from the 1.38, as an intermediate product. And just like you've probably looked at aerosol optical depths, we make the same thing from the 1.38, and that you can see we get down to well below 0.2, which are aerosol-like levels, and the instruments work so well, it's very easy to do. So that is my last slide. These are my takeaways, or I guess these are giveaways. It's up to you to take them. But the points I tried to make were, I think, if you take the time and zoom in on the low reflectance values ranges of the 1.38, you'll see a lot of details that you're missing in the default AWIP scaling. I know this is subjective, but I really do think the 1.38, of course, during the day only, identifies those thin cirrus features much more easily than any other channel combination. And to boot, anything that gets lofted into the atmosphere, be it smoke or dust, the 1.38 is your best bet. And so for some of those things, it's your only bet because they're invisible in the infrared. I tried to show you that, you know, it could be used in conjunction with other visible channels to differentiate where low smoke is going if it's obscured by cirrus, as well as if it's low smoke versus high smoke. And if RGBs are of interest, I demonstrated 2 of them that make use of the 1.38 micron, I think, effectively. And one is that modification of the day cloud phase that we call the day cloud type. I should say also, I learned that Sierra has a snow cloud layer RGB. It's a little more complex, but it does use the 1.38. And I couldn't actually, I couldn't make it to its true, couldn't get it to look right, so I didn't show it. But that's another, of course, option for getting the 1.38 in front of you. So my takeaway is just, again, the 1.38 is it's been around for decades. It's not going anywhere. So I hope you can take another look at it and see if it can get used a little more. So with that, I'll end, and I'll leave on the slide here. There's plenty of information that people, I guess, at Sims and Sierra have made about this band and these RGBs. And I forgot to mention, there was a case study using the 1.38 micron band and looking at cirrus forming over a Mexican terrain by Ghost Grasso and Soki. Anyway, yeah, that's it. So thank you very much.
All right, thank you, Andy, for a very enlightening presentation on a channel many of us aren't probably too familiar with. So before we move on, I want to encourage all attendees to stay on for the discussion section of this week's presentation. We also want to highly encourage participation from field offices and regional headquarters as well. Please feel free to complete the feedback survey that will be posted in the chat room very shortly as well. In a week from today, on Thursday, October 21st at 12 p.m. Eastern Time, Dr. Jim Yo, NCEP's Chief Administrative Officer, will discuss satellite data assimilation. I also encourage all attendees to contact the TowerS team of Lee Byerly and Kashad Bowman for questions about the SBC or for the configuration of satellite products. More information will follow in an email from the TowerS team coming up. So I got one question for you, Andy, as we move on to the discussion section here. Something that we've talked about in our past severe weather workshops and stuff like that is the ability to track above anvil cirrus plumes. We've documented them in recent literature as a noticeable and trackable feature with severe storms. In your opinion, Andy, do you think the 1.38 band offers much detection and tracking capability with these features for severe weather situations?
Thanks for the question, Chris. Yeah, we did. That came up, and that is an important thing. I have to say, in the 2 examples that I looked at, it really didn't, because the 1.38 physics needs, you get separation not by temperature differences in the infrared, but by water vapor being between you and the feature you want to distinguish. So when I looked, I mean, there's not enough vertical space between the above anvil cirrus and the anvil to differentiate the 2, and the 1.38 behaves just kind of like another visible channel. So
understood.
If that cirrus moves out over the anvil, you'll see it very easily. But I think in that above anvil case, no.
Okay, all right, very good. All right, so I see that Lee has also shared the link for the feedback form for the SBC. Also, I'm going to go ahead and post the link from a Colorado State Visit Training article on using the 1.38 band, so you guys will all see that within the chat room here in a second. and we're going to see what other questions we might have. So I think there was several questions with regards to the RGB that you showed, Andy. Let me see if I could find them here. Let me go back up. All right, so Steve Zubrick, the Sioux in the Washington D.C. office stated something along. He said provides this. The RGB seems to provide more clarity in discriminating sears. That's for sure. I think that really popped out. Somebody else asked. Let's see. Let me go back up. Are there any trade-offs from the day cloud phase distinction RGB besides the cirrus really popping out more? Andy?
Well, I guess, you know, that's the positive, right? So I guess I would ask the question of the question would be, does the removal of the 11 micron, what information is that providing? So, you know, and I think the cirrus, you know, will the obscure features that you're used to seeing from the evolution of the 11 micron image? I think there's been some discussion in here. So I think that could be the downside if you're looking at convection and there's information being given by the temperature growth or decrease from the 11 micron that you know might be obscured if you move to the 1.38. Certainly
Sure.
you'll see the glaciation that won't be impacted because that's from the 1.6 channel. And I mean, you will see the clouds getting redder as they move up in the atmosphere, just because there's less water vapor above them. So yeah, that's an open question. I think that's a subjective one that people who are knowledgeable of using that cloud phase RGB would have to address.
Sure, understood. Okay, Scott Lindstrom also asked the question. He wants to know, for the cirrus case over the Atlantic that you showed, Andy, what would that kind of cirrus deck look like to a person on a boat in the water? Would the sky appear white, or would it appear mostly blue? Would you be able to see them, etc.? Any insight on that question?
No, I don't. That's a good question. No, so Dan Lindsay sent me some Martin Sedvac. He takes pictures on the ground and compares them to satellites, and he did this for some VIIRS scenes. We also had very just widespread, very thin cirrus, and it was kind of a white sky.
Okay, understood.
Yeah, that's a good question, Scott. It depends on the optical depth, and those are pretty low. So.
And Jordan asked, have you looked at a trend of the 1.38 micron reflectance compared to 11 micron brightness temperature? That would have a consequence of how it is integrated into an RGB.
No, that's a good point, Jordan. I think they would be correlated though. As a cloud mass moves up, it's going to get colder, but it's also going to get brighter in the 1.38 as the water vapor above it diminishes. So no, I've not quantitatively done that, but that should be done.
There's also some discussion about like the operational applicability, for a forecaster at a forecast office. It looks like, like doing sky grids within GFE and stuff like that. Some pretty interesting discussion here as well from Aaron. I think Bill Lyon actually asked the original question. Can a forecaster speak to the day-to-day operational significance of a thin cirrus layer that's trackable via the 1.38 band or the RGBs that you created? And Aaron responded to Bill, I would say it's kind of a minor and not much impact, but when a forecaster is doing sky grids, knowing when there are high clouds over an area to improve the forecast and the public of what the public sees and hears, as obs may say clear, but when the sun comes up and there are high clouds over the area, like I said, it's pretty much minor impacts, but still it does have some type of, I think what he's trying to say is that a perception to the public who may be, looking at a weather service forecast and going outside and seeing, a cirrus up there as well. So I think it does have some impact for sure. So trying to see if there's any other questions here. Let's see here. I'm not seeing any at the moment. I guess we can go for like a last call here. Anything else? Does anybody have any additional questions that anybody would like to type in real quick?
This is Jordan. I think one thing, I don't know if anybody from our field offices wants to comment in the chat or just speak aloud. Really curious about whether or not people would like to see the cloud type RGB in AWIPS to complement the cloud phase RGB. Is this something that you think? I see Aaron Jacobs saying yes. And there was also that other RGB, I'm forgetting the name of it now, that Andy was showing over the polls. You know, if you could just type yes into the chat. I don't think we have enough time to get a poll up and running, but yeah, another thing that Steve Zubrick pointed out that I think is sometimes also not necessarily commonly used is the ability to change the scaling in AWIPS. And it's been a little while since I've been in AWIPS, but I believe if you click on the product legend in the lower right corner, when you have a single band loaded and you go to change color map, you can actually change the scale values. And there's also a way to change the individual components for RGBs as well. Maybe somebody in the field or member of our Tower S team can shed a little more light on that if you'd like. Okay, Mike said I had it right, so glad I'm still holding on to things.
All right, I don't think I have anything else. Let's see, any other questions coming in here? See, Dan, yep, Jordan's correct. I think I got everybody here, Jordan.
Okay, well, we can certainly wrap it up there. I thank everybody for attending today. Really appreciate the presentation, Andy. Absolutely valuable to hear about the 1.38. It's a band that's not been on previous generation of GOES, and I think for that reason, sometimes overlooked, but there's some value. And I've always joked about when I've done the SU training, you know, we all get calls in the forecast office about chemtrails from time to time. There's no band that shows you those better than the 1.38 micron. So make sure you send those callers over to the STAR website so that they can get really scared. Anyway, that's a joke. Next week, we're going to have Jim Yo talk about satellite data simulation, and that's a huge topic because so much of the satellite data, particularly from polar satellites, is a major contributor to forecast accuracy, and you might be very interested in those data sets that are going in to the models. So please join us next week, Thursday, October 21st at 12 noon Eastern time. And in the meantime, contact the Tower S team. I think we are, based on the feedback that I've seen, we're going to try to get this RGB into an RPM. So hopefully you'll see that in your field offices in the near future, and you can provide some more comments. But if you have anything else related to satellite imagery and AWIPS, get in touch with our Tower S team, and they're certainly standing by to help you. With that, hope everybody's staying well. Thanks again, Andy, Chris, Kashad, for all of your help today. Great talk, great questions, and thanks all of you for attending. Take care.
Thank you, everybody.